iPad and got that stuff. Okay. So, I think what we need to do here.
Did you bring the practice or the retake exam?
Yes, I did. Thank you for reminding me. Thing is, I corrected them, almost a week ago. I've forgotten about them already. All right, let's get those out. Max isn't here. Sebastian? He's here. What's that?
What's your favorite problem to put on the final?
Let's see, what problem would Matt would really hate?
I would really hate single phase power.
Yeah,
Don't put that on my
that'd be
face.
terrible.
Transmission lines.
Oh, you heard of
Luca is not here. Ryland is here. Pass this back to Ryland, will you? Pass this back to Ian. These two. There you go. Give these to Din in the Seattle shirt. Let's see what else we got here. Amy is here. Grant is here.
Yeah, I was just
And Austin is here. Okay, guys don't bring to the final, I guess. Okay, I messed up a bit on the first problem. The first problem in my retake I had worth 22 points. The actual problem in the test was worth 33. So if you look at the front page there, the lower right-hand corner, you'll see that I multiplied by 1.5, and that's the poor score I put in. So I took whatever he got and just multiplied it by 1.5. Peter, I see you after review today. You sure? Can I see you after the review today? You should be nervous. Everyone should be nervous all the time. Mike? Okay. Sorry I didn't have those on Monday. Just a stupid oversight on my part. So what I want to do first is I want you to look at the final exam study guide. So take a look at something I handed out some time ago. There are a few of them. There's one I think still here. That's it. Okay. So it kind of goes through what we did this semester. Materials from exams 1, 2, and 3. Single phase power, 3-phase power. Those sorts of things that show up on the exams, finals, quite often. There's a single phase power problem and a 3-phase power problem. Sometimes it's folded into a transmission line problem or something else, things of that nature. So, if you look at this, homework 1, energy sources, that sometimes shows up in some closed book stuff, but not that often. The bolded, notice that the single phase AC power in problem number 4 here is bolded. The 3-phase power on number 5 is bolded. The reason they're bolded is that's if you have limited time, you want to spend some time on that stuff. Because in the end, that's kind of the most important stuff you learn in this class. It doesn't matter what you go into, even if you don't go into a field of power, if you're in any sort of a situation where you're in an industrial place or somewhere where you might come into contact with power, if you are the electrical engineer that knows a little bit about it, you will have questions. There are no questions about that. It's just my head.
No, you're good.
magnetic circuits rarely show up. Transformers, not as likely. One-line diagrams, per unit stuff, not as likely. Synchronous machines, not as likely. Induction motors, not as likely. You should know the basics of all of this stuff and where to find the material in your cheat sheets and things. Not covered in previous land. Oh, transmission line, we actually did. So that's, you can take that out as a super duper likely thing. These probably should not be bolded. Power flow, transmission line faults, protection, virtually certain to be on there. But notice I'm kind of missing the problem here. I would like to have at least 4 problems on the test, they're most likely. So I'll probably put 1 in from induction motors or synchronous machines or something like that. But I don't know what, and I haven't made the test yet. So at this point, what I'd like to do is basically open it up to questions. And if there aren't enough questions, we'll just pull up fall 24 test and go through it. Yes, Bob?
Fall 21 final question 2 part F.
Well, let me get fall 21 final up first. That is number 1. And I'm hoping that you got my message. There was a problem on the, I think, fall or spring 23 exam. There was a problem with the answers. Got that corrected. Does it show up? Yep, it does. Good. Luca, I have stuff for you. Let's see. So fall 21. I don't know if I want to open it with that. I think I want to open it with this other problem. I don't know why necessarily. Which problem?
Problem 2 part F, please.
Part F. Well, I'm probably not going to do just one part of the problem.
No, I
I
just
want
want
to
to
go
go
through it.
I would really not like to see anything else on
I'll see the other stuff.
Me too.
Yeah, I would love to go through the whole thing. Okay. Oh. For those of you at home, do fall 21, problem 2. 3-phase, delta-connected induction motor has the following equivalent circuit components. R1 is that, R2 blah, 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 and I put them all down on that schematic. Sorry about the lights over there, but I want to have a decent lighting over here, and I don't seem to be able to do individual boards. So, question then is, let's see, draw the circuit of one phase and label the known parts. What did I do? I put the answers up, didn't I? That's not what I wanted to do. I wanted to put them to the test. Okay. Is that the answers? I think so. Let's see.
Hey, Lauren,
Yes, sir.
do we just have the 2 hours for the final then, or how is that going to work?
Okay, we're going to start at 3:30, normal time. There's nothing else scheduled in here after 5:30, so I'll probably just let you run
Okay.
until we have 1 or 2 people or 3 people left, and then I'll try to get you moving out of here.
How long does it typically take to do an iron final?
It depends on who you are. Depends on who you are. Because the finals are set up to be basically a 2-hour final, but I'm not going to rush you, so people take their time that way. Instead of rushing through the problems, they're just going to meander through and take their time, think about it, that sort of stuff. And that's kind of how I want you to approach the test. So it's kind of hard to say because, yeah, you should be able to do it in a couple of hours, but if you're taking your time and you're meandering along, then that takes a little longer. Okay, so where were we here? Yeah, this is language.
You can't touch my baby.
Okay, so you need to draw the drawing for this thing. And hopefully you have that pretty much memorized. If not, you know where to find it in your notes. If it's not in the notes, you put it in the notes.
So we have a resistor and an inductor, and typically just an inductor down this way. And we have, I like to split these two into two pieces, one of which is R2 and one of which is R2 over S1 minus S. S minus 1.
1 minus S, yeah, 1 minus S.
And then we go to X2 over here. This is JXM, I believe. Yep, M. So this is 15J ohms given to us. R2 is equal to 0.2 ohms. R1 and X1, I take that back. R2 is 0.05 ohms. This is 0.02 ohms. JX1 is J times 0.4.
It's just 0.2 ohms for R1.
Like that, right? Okay. Currently running at 1710 RPM. XM is 15. Anything else? Oh, X2, 0.62. 6. Yeah, 6 ohms. 1710 RPM is what it's running at right now. So that's my model. That's part A. Part B, find the slip. Okay, what is this likely to be? How many pole motor?
1800, so.
Yeah, and it's probably the synchronous speed is 1800 RPM, so 4-pole motor in that case. So it's 90, basically we go this way, V, 1800 divided minus 1710 is 90, 90 over 1800. What does that turn out to be? Yeah, I think it's 5%. 5% or 0.05. Okay, good. Output shaft torque is 60 Newton meters. Find the output power. Okay, that's not that hard. C. 60 Newton meters times the speed, 1710 RPM. But what are we going to do for this to make it into radians per second? Yeah, it's either pi over 60, or you can actually do it because you know that 3600 RPM is 377. But if we do this, that'll work. It's 2 pi over 60, right? Yeah. And we end up with power. What is the number? Good one. I have the answers all worked out. This is 1221. Okay, the answer comes out to be, what, 10.744 kilowatts. Okay, C, D. D, mechanical power losses all lumped together is 400 watts. Find P convert. Okay, which way is the power flowing through this motor? From where to where? Input power is what? It's a motor. That's not a hard question. What kind of input power do you put into a motor? No, I'm being more general than that. Electrical power. What comes out? Mechanical power. We just found output mechanical power. So in between those two, there's some losses. There's some losses in R1, there's some losses in R2, and there's some what's the other loss? Rotational loss. So if we want to find the converted power, we have to add this to the output power to get the converted power. So P convert is equal to 10.744 kilowatts plus 400 watts gives me what? 11.144? Like that. If I wanted watts
watts, otherwise I put it in expression in kilowatts, doesn't matter, as long as your units are right. So we add 400 watts to that. Find I2. Okay. So what component in this drawing represents that P convert? R2 over S, 1 minus S times 1 minus S. So what I have to do is I have to say, okay, I know how that works. E, this P convert that I just figured out is also equal to I2 squared times R2 over S, 1 minus S. Can I solve that for I2? Yeah, I just back it out of there, you know. Solve it for it, it becomes the square root of, let's see, the square root of P convert times S divided by 1 minus S.
And S is
Times R2.
S is 0.05. Yeah.
S is 0.05. So it's 1 over 0.05 times 0.95. So not too hard to do, and you can come up with the I2, and the I2 I come up with is 19.774 amps. Amps, 19.744 amps. Anchor, Mike, Max, I've got something for you up here. Takes care of them all. Okay, so that figures out the I2. And F, isn't that what the one you were talking about, asking about?
Yeah, following.
Okay. Find the line current. Don't try any shortcuts here. You need to do your math with full complex numbers. So I'm giving you a hint here. So I advise you to assume that the phase angle of I2, we just found that 19.744 amps, 774, I'm sorry. I didn't look at my own handwriting very well. 774 amps has 0-degree phase angle. From there we can move forward. So together, these two are how big? R2 over S. So together they are R2, which is 0.5 divided by 0.05. I think we can figure out what that is without a whole lot of trouble. What is that? 10. 10 ohms. Okay, 10 ohms. So we have 10 ohms here, and with that we'll have the 0.6. So what can I figure out from that? I can figure out, let's see, EF. I can figure out that E1 as a complex number is equal to 19.774 amps times 10 plus 0.6J. So it doesn't have a huge angle, and it's almost exactly 10 times that. But it'll come out to be 200 and, nope, what am I going to do with it here? I came out with a rectangular number here, and the rectangular number is, easy to see, 197.74 plus 0.6 times this is 11.865J volts, like that. So that's that guy. What do I need to do now? Well, I need to figure out how much current's going to flow down here, because if I know the current here, and I know this current already as 19.774 at an angle of 0 degrees, I can simply add it to this. From that, I can get the line current like this, or at least I can get I1. I1 like that, and from that I can probably figure out the line current looking back to see how this motor was originally connected. Okay, so what I want to do now is come up with E. Is that E1 or E2? I forget what we call that. E1. E1 over 15J is going to be 19.774 197.74 divided by 15J plus 11.865J divided by 15J. What happens to the J's?
Cancel out.
Cancel out. So that becomes my real part. My real part is fairly small. By the way, is this legal to do?
Yeah.
Can I do this division? Can I divide each one separately by the 15J? Yeah. Okay. You got to watch that a bit. Sometimes there's some mistakes you make with your fractions. This J, when I take it on top, becomes what?
Negative.
A negative J. This kind of screws you up a little bit because the J part now becomes negative. Which makes sense because the current through an inductor lags. So now we have to take this piece and this piece get added together to figure out what the imaginary part is. This piece and this piece gets added together to figure out what the real part is. Now, I didn't actually go through all of the numerics here, but I came up with the result is, oh, I only figured out the magnitude of the result. So let's see. I'm going to do this way. It's a little bit screwy. But, yeah, I did it all in one step, pretty much. So anybody have the numbers here, what this turns out to be?
The E1 over 15J.
E1 over 15J, yeah.
0.79 minus 13.18.
Okay. 0.18?
Yes, 1/8.
So that's this piece. And do I believe that? Yeah. 197 divided by 15 is 13. Yeah, that's close. And that would be a little under 1. Yeah, so that makes sense. Okay, so there that is. And what I need to do now is add that to the current right there. So I'm going to add that. So I'm going to add 19.774. And I'm going to end up with 20. So this is I1 is equal to, as a complex number, 20.465, like that, minus 13.18J, like this. Did I do that right? And then what I can figure out is I1's magnitude. So if I need to figure out the magnitude, I will do that. Like that. And then I gotta look, because this is a three-phase induction motor, right? So before I answer that as my answer, what else must I do? Whenever it's a three-phase problem, when you end up with an answer of current or voltage, you better look back and see how things are connected and where you are actually answering the right thing. So let's go back over here. I think it was a delta connected motor. And that's not at all uncommon. Mike, how many times have you hooked up motors?
Too far up.
How many times have you hooked up motors?
A handful of times.
What's more common? Three-phase motors, I mean. What's more common, delta or Y? What do you? No preference. Bob, motors at the refinery where you work, what are they often connected at?
They're typically connected to delta.
Typically connected to delta, yeah. Most motors are. Because you get a little higher voltage and lower current through your wires. Let's see. Insulation is cheaper than copper. So what gives the connection here? Delta. Delta. So I have a current right here. What do I do to get that to current to be delta current instead of? Yeah, I gotta be. Yeah. What I gotta do is this is one part of a delta, and because there's two currents being added somewhat together, I have to multiply that by the square root of 3. Equals I line magnitude, and that I line magnitude is then going to be 42.31 amps. Okay, that's part F. Questions about that?
So it's basically circuits. And there's an awful lot of circuits. You can't do your circuits. Continuing on, G, find P rotor copper loss. What part up in this drawing is responsible for the rotor copper loss?
Just R2.
Just the R2. The R2 that's driven or drawn horizontally up on top. So what do I do to find my rotor copper loss? This is E, F, G. P rotor copper loss is equal to, we're back to I2 magnitude, the 19.774 amps, squared times 0.5. Is that it? Yeah, again, it's a three-phase problem. We got to ask ourselves at the very end, do I need to multiply this by 3, or divide it by 3, or multiply by the square root of 3, or divide by the square root of 3? In this case, it's a power thing, so I need to multiply by 3. If I take the 19.774, square it times 0.05, and multiply by this by 3, I end up with 586.5. Good. A, B, C, D, F, G, H. H is next. I think there's an H and an I. Where is my H? H. Are we still at the top of the problem here? Yeah, we are. Go back down to the bottom. H. Stator copper losses. How do I figure out the stator copper loss?
I1 squared times R1.
Yeah, where is I1 squared? Well, an I1 squared is this mess, right? I1 is that mess. So it's literally 20.564. Plus 13.18. Is that I1 squared? Think about this. Yeah. So, because you square root that to get I1, so if I don't square root, I'll get I1. So I'm going to put it up that way. Times, which resistor? 0.2 ohms. And again, what do I need here? 3. Yeah, a 3. When I figure that out, I end up with 358 watts. Last question is, what is the efficiency of this system? Well, we have all the losses accounted for, right? We know what all the losses are. And we know the output power. So it should be fairly easy. What's the output power? Yep, 10.744. Plus 10.744 plus, actually I don't need this because I've already figured out the peak converted, haven't I? Which is 11.144. Comma, let's keep it all watts. 11.144 plus, what else? What do I have you figure those two out for?
Those are also losses.
Plug them in here. 586.5 plus 358. These are all watts. And I end up with an efficiency that's not very good. 88.9%. Like that. About 88.9%. Not super good. But then I will make some of these values unrealistic and bigger than they should be, and the loss is bigger in order to see if you're calculating things out right. Although for a motor, I don't know that 89% is all that bad. It might be in the ballpark. Bob,
Yes.
did I answer your question?
Yes, thank you.
Yes.
Can you do a little explanation on the green sheet of how like the Y delta connected transformer part works and stuff?
On the green sheet, are you talking about the default stuff?
Yeah.
Okay, let me pick that up then, quickly. Okay, we are talking, let me get that into place. Okay. This is a bit messy, and you had to deal with it a little bit in your homework. I try to generally avoid it in the test, but now that you're going over it.
Oh, no, never mind. I don't want to go over it.
So, there's an interesting thing we have to remember about the zero sequence, and this is all about the zero sequence here. It's not about the positive sequence, it's not about the negative sequence. It's all has to do with the zero sequence. So the zero sequence transformers. A zero sequence, right away, there's already a weirdness, a zero sequence in delta and y. Where the heck? Can't find it. I can't see. Oh, I thought it was up there, but there it is. So let's go up here, zero sequence impedances. Anything that is hooked up in delta, anything that is hooked up in delta. Now are you, let's see, are we on here? Oh, you can sort of see it. I don't know. If I hook anything in delta, and that could be a primary transformer, it could be a load, it could be a motor, whatever I have hooked up in delta. If I have all of my three voltages here, but all three are exactly the same, can I get any currents to flow? So in that case, what does anything hooked up in delta look like? An open. Yes. So in the zero sequence stuff, this always looks like an open. And that's why I've said delta equal open. Okay, how about y? Well, if I have things hooked up in y, there's two possibilities. If there is no neutral connection, can I get any currents to flow? So any Y-connected item that does not have a neutral connection also looks like an open from the zero sequence point of view. The only alternative now is if I have, in fact, some, and I put in a grounding impedance, which normally doesn't show up in our schematics because we don't care how good our ground connection is, and literally that is physically to ground, because how much current normally flows there? Pretty much zero. As long as we're balanced, if we act perfectly balanced, it would be zero. But we're often pretty close. So that current's fairly small. Now we may have to consider this. Now it's a completely different story. Now can we get currents? Now remember, all three of these voltages are the same, and we're assuming that there's a balanced load or balanced thing, whatever. So how many currents flow together into the ground, and are they all in phase with one another? So can they simply be added? Because they're in phase, they can simply be added. So if this is I line for phase A, so this is A0, I guess, then this would be 3IA0. Oh, by the way, it may not be IA0, maybe whatever the current is. So now what does the impedance look like? Well, that's difficult to deal with, but can I say that the voltage across here with 3 times the current would be the same as the current, one current, and 3 times the impedance? Is that legal? So when I only want the A phase, what I do is call this ZL, ZL plus 3 times Z ground, like this, and that's what it looks like.
some kind of sense?
So I have another question kind of about it. Why on the homework model does 0 as a short?
Because the fault was to the right of that generator and transformer. The fault was to the right, and we have to look at it from the fault's point of view, so we're looking back in this way. And so that was, I think, a Y-connected,
A Y delta.
yeah, no, it was a delta Y, I think, so the Y was on the fault side, and it had a connection to neutral, or to ground. So it would have been this.
So why is there not like ZL?
Okay.
CG?
The ZL is the X of the transformer that is still in there. So if you look at it, the impedance of the transformer is still there. The per unit impedance of the transformer. That's the load, XL in this case. But it doesn't have a 3 ZG. And the reason for that is because you were not given any impedance to ground. So what is the worst case assumption you could make for your current sizes? That it's straight to ground, it's 0. In fact, that's not uncommon. That you would go, I don't know what that impedance to ground is. Worst case, it's nothing. So that's the biggest currents that could flow. So let's assume it's the biggest currents that could flow. So it's not at all uncommon to not even bother with that ground impedance. It's kind of interesting to look at how it fits in, but it's not always there. But that's the reason why. Because you have to look at this from the fault's point of perspective. That's how you look at it. Because whatever 0 impedance currents, or I'm sorry, 0 sequence currents there are, occur because of the fault. And so that's where they're at, not in the generator. All right, so now once we have that idea of how the impedances work there, now we can start looking at transformers as well. And there we go. Transformers. Any delta connected primary, you just consider it an open, bang, done, full stop. Y connected primary. Now primary, you got to be careful. Primary is on the side of the fault. It may not be the original primary from the way the power flowed. So maybe that's a poor choice of words there. No neutral Y connection on the side of the fault. I think I should probably go in there and change that. Instead of saying primary, say on the side of the fault. On the fault side, whatever. Y connected on the side of the fault. If there's no neutral connection, it's an open, just like the middle one there was before I put the CG in. With a neutral connection, now you gotta look at other stuff. And rather than go through the little rules there, let's take a look at it here. It's Y. If the fault is on the left, it looks like an open. Can't see it. Yeah, there it is, right there. It looks like an open. If the fault is on the right, it also looks like an open. Let me get my stupid laser pointer. So we're looking in the notes on page, what page is this on the notes for those who are looking at the video? There's not too many that are going to look at the video. I think maybe Nate, that's it. Mr. Krieger. Okay.
14.
Okay. Sorry, this is not very easy to see. Y, it's open from either side. If the fault is on the left, it looks like an open. If the fault is on the right, it looks like an open. Here, Y with a connection to ground here. If the fault is on this side, why is that going to look like an open? Didn't we just say over here that if we've got a connection to ground, we're going to have currents? What does that mean? Okay, why would that look like an open from the left side? Okay. This is still 0 sequence stuff. These voltages have got to be the same, right? So can I have any current? Well, what are the currents going to be? If If this were in fact connected to ground, there would be a current here, or a current that way, however you look at it. But this has got to be the same, and that's got to be the same. So is there any currents in these windings right here? If there's no currents on the secondary side, can there be any currents on the primary side? Because they must be related by a turns ratio, right? Or 1 over the turns ratio. So if I can't get any currents to flow here, I can't get any currents to flow here. That's why it's open from both sides. Now the only time you get something is when you get things to neutral on both sides, connections to neutral on both sides. Then you get this weird thing where whatever the impedance of the transformer is, that's weird. Where does that come from? Well, now these currents got to flow in and all go through here, so that's why that's tripled. That's why that's tripled. But these currents are actually set by these currents over there, and they all go through here, so that's tripled as well. And that is the remaining impedance, because this takes care of both sides' coils' impedance. But why doesn't it go to ground, like it does over here for a load, right here? Well, the reason it doesn't go to ground is because these currents are basically set by these currents, and it looks like something where the current goes through it when it's all in per unit. So that's how that works. That's a little harder to see, but it's one of the few that isn't just totally open. Oh, okay. Well, this is interesting. What's missing here?
On the notes, it's not missing.
It's not really missing on the notes? Maybe it's just the way the projector did it. Okay, well that's bizarre. Okay, here it's open, no problem. Here, this is, these currents can go to ground, but these guys right here, they cannot flow because there's no difference between VA and VB. So there's no currents flowing here. There's no currents flowing here. No, I take that back. You would think not, but they can do this. And that's why that looks like a short. Therefore, the transferred impedance over is also 0, and this just looks like a simple load like this. And then finally, the last one, delta. Delta is an open. Now, I don't believe that I put all of those on the green sheet. I just put the 2 that are important. The rest of them are basically all open. And that's where the 0 sequence stuff differs a lot from the positive sequence and the negative sequence. Is the 0 sequence impedances are a bit harder to figure out. You got to work on them somewhat. And to be completely honest, it's one of those places where you might actually be called on to do something like that. Somewhere, distant future. When you've gone up the ladder a little bit, most likely. Of course, it's another thing that if you come into a place to work and something like this comes up, and you can raise your hand and say, hey, I know something about that. What does that make you?
The expert.
Not necessarily. What's that, Natalie? It makes you more valuable to them if you're actually telling the truth. But always being a more valuable employee is a good thing. Especially when it comes time for layoffs, which always come. You guys are young, you don't understand that necessarily. You have no job. It is very, very, very unlikely that you'll have one job the rest of your career. A little bit more if you go work for, say, the power company or something like that, and you want that, and you like that type of thing. But many of you will have multiple jobs, and you won't necessarily want to go back on your trade. All right, what's the next question? Did I answer your question first, Everett? Yes.
I want to do the whole question, but I just have like a basic question.
On?
It's really stupid. It's like a transmission line. I think it's like 1223.
1223?
Yeah.
All right, let me
I
pull
just
the
have
phone.
one question.
Okay, maybe I can answer that one question and we can move on. We'll see what other people want to do at that point. You said 23, right?
Yeah.
Oh,
quickly, as long as I've got this up here, this is not untypical of the kind of questions that I ask having to do with protection. And there's typically one of these questions right here on the timing. Ishar, do you have homework 1? Homework protection? You don't have it on you?
I did.
Well, what I was going to ask is, do you remember what I told you the answers were to that part?
Oh, yeah, actually, I could pull it up.
Okay, tell me what the answers were. You had a question on your homework similar to this curve over here. It's, similar to that curve, and it doesn't matter how hard I press the side of the chalk, it's not going to make a red line. So similar to this, and it's very, very, very likely that you will get a problem like that on the test. So let's make sure you have the answers to the one in the homework. So which problem was that, Ishar?
That was problem 9.
And what were the numbers?
A was 0.09 seconds, B was 0.04 seconds, and C was 0.02 seconds.
So you may want to write those down so you know you're getting the right answers from that curve. It's a simple, just a time-like curve on a breaker. It's actually, if you know that breakers have time curves like that, you're halfway home in most job interviews. Because at least you won't look like an idiot if they ask you about that sort of stuff. Okay, going forward. I don't know how to transform a problem. You're almost certainly going to get a problem somewhere like this having to do with power flow. Very, 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 very likely. Should I put another very in there? I would just screw the varies and say it's certain. You are going to get a problem like this.
Hey.
Let's see, what else?
And this one can be like 90% of the points.
It might be 90% of the points you get. Yes, Andy.
Which test is this?
He opened himself up to that, didn't he?
Which test is this?
Fall 23.
Okay.
Okay. This is a typical kind of fault problem.
Do I do this one next?
The fault problem?
Yes.
Sure we can.
Yeah.
This is a typical kind of fault problem. Notice there's no impedances on the right side of the fault. That's just to make things a little easier. And all of the impedances on the left can be lumped together. See how that works? So I've tried to make it a problem that isn't too hard. I don't put too much junk in there, so let's see what else. Let me do this. I can't find my stupid mouse again. I'm always losing this thing. Oh, there we go. Yeah, I actually have to find it on my screen and then move it over. Okay. This is the transmission line problem you were asking about, right, Madeline?
Yes.
Okay.
Okay, so my question is really dumb.
Okay. I
On
didn't
part
say
A, it says the line voltage at both the sending and the receiving end are both 230 kV. But I
Okay.
remember like when we took the exam, that did not mean that the receiving end was 230 kV. So would the receiving end be 230 kV at an angle of 0 degrees?
It depends on which one, where you have other information, where you're going to start your calculations. Because usually you want to make the place where you start your calculations to have the 0 degrees and work from there.
Oh, okay.
So those two 230 kVs, they can have a line voltage of 230 kV, but they are not going to be the same phase angle.
Okay, so
Because
maybe-
unless the phase angle of the sending end leads the receiving end, there's no current. Okay, go ahead. Sorry.
So would I make like the power angle for the receiving end negative 12 degrees and then the power angle for my sending end 0 degrees?
They would not be, a power angle is the difference between those two angles.
Okay.
So if the angle of the voltage at the sending end was 0 and the angle of the voltage at the receiving end was -12, then the power angle would be 12. But that could also be figured out from a sending end voltage that was 6 degrees and the receiving end voltage that was -6 degrees. It would still be 12 degrees power angle. Or the sending end voltage is 12 degrees and the receiving end voltage is 0 degrees. Either one, all of these come up with a power angle of 12 degrees. So the 12 degrees is the difference between the two angles of the two voltages.
So I could pick my favorite.
Let's see what we have in this particular problem. What are we given? So choose the most appropriate model. You're supposed to draw the model. That's not too hard. You've got it in your cheat sheet. Basically copy and paste and put numbers. Most of us would be better off drawing capacitors where there are capacitors. Keep in mind what the current looks like. Again, there's no J on this one. You have to know that there's a J that goes with that. Okay, the line voltage, both ends, sending and receiving are 2 degrees. The power angle is 12 degrees. Delta is 12 degrees. The load at the receiving end is 93 MVA. The power factor is 0.95. Judging by the voltages, the load power factor is most likely leading or lagging. Okay, if we have a fairly significant load like that, and we have similar voltages at both ends, or even a higher voltage at the receiving end, we probably have a bit of capacitance at the receiving end. Because it takes capacitance at the receiving end to keep the voltage up. And it's a fairly long line, isn't it? 200 kilometers, yeah, it's a fairly long line, so there's going to be a lot of reactance in the line. So in this one, it's going to basically have some feeling for it that it's likely to be leading at that end. If you go through the calculations, you find you can't do it without like negative impedances or something like that, if you choose lagging. Find the current to the load, not I line as a complex number. So where are we going to start our calculations? At the load end or at the sending end? Receiving end or the sending end?
I started at the receiving end.
Receiving end. So what makes most sense to call 0 degrees?
The receiving end.
The receiving end, yeah. That is exactly what I would do. I would make the receiving end VR 0 degrees. Is VR equal to 230 kV?
I hope so.
Pardon?
I hope so.
Anybody else want to give any answer?
What's the other answer?
What's the other answer?
No.
Oh, 230 divided by.
There you go. It's 230 divided by √3, because our picture is a single phase, and the voltages are line to neutral voltages, VR and VS. So we have to take that 230 divided by the square root of 3. Then we can say that you're going to have a 0 degree phase. All right. Anybody else want to go through any of this? It's a transmission line problem. It could show up on the test, but it's not all that common. It's not likely because you've already done one. It's no more likely than anything else. Yes?
I have another question about the test.
Oh, I've already been asked for the fault problem.
Oh, sorry.
So we'll probably do that first and then come back to these. All right. Are we finished with the transmission line problem? Is there anybody else who wants to ask anything on this? Have I made it sufficiently unclear? There it is. All right, so I've been asked about the fault problem. Notice no transformers, no other things. I'm not trying to make this super duper hard. I want you to be able to show me that you have some idea how to handle this. And I don't think I've ever put a transformer in a test problem. I have in the homework, but not in a test. So this would be the first. Just to make everyone happy. One phase of a balanced three-phase system is shown here. Fault occurs at point F. It is a short between lines B and C with an impedance of ZF. Okay. Throughout the circuit, you would have to analyze and find the fault current. Identify the parts and include the component values and currents at the fault. Set up the mathematical expression or expressions to find the fault current.
don't forget J and the default current is not IA1. Then the default current is not IA1. Okay, so what we have is a single short between lines B and C. Okay, short between lines B and C is the one we have. So, first, there's pre-fault stuff you sometimes have to go through to figure out what the E prime prime is if you had the E, and what the X, well, and X prime prime. Do you have any of those numbers or anything like that? So all you have to do is put down the right symbols on the drawing and you'll be fine. You don't put down E on your drawing, you put E prime prime. You don't put down XS on your drawing, you put down X prime prime, XS prime prime. Okay, so that's the only thing you have to deal with for that. Sometimes, I think last fall, one of those, I don't know, I actually had some numbers and you had to figure that part out. So, okay, so how do we figure out what the schematic looks like? With the little green sheet. So let me go find that and bring it up, or bring up something similar, and we can put it together. So again, I'm not expecting you to memorize all that stuff. And one more time, if you don't find something on there that you think ought to be on there, that's why you have it earlier, so that you can put stuff on there. Let's see, oh, where the heck is that drawing? I think it is... Okay, there it is, I think. Oh, heck, no, that. Where is it? Oh, there it is. Okay. All right. So you have that drawing right there. Which problem is it? Which one of them is it? The line. Lines B and C with an impedance of ZF. So it looks like it's like the dead center one there, isn't it? So what I'm going to do is I am going to try to figure out how to do this again. This is not what I wanted. This is the PDF. All right. Well.
Draw it on the board.
Yeah, I think I'm going to draw it on the board. All right. I'm about to erase the induction motor problem. Is there anybody who wants to take a picture of that before I erase it?
How do you know it's line to line?
It says that. It says lines B and C are shorted in the problem.
Oh, okay.
Anytime you have a question like that, go back while you read the problem. Often the information you need is right there. Suppose I could use a bigger eraser. Put it on faster. There it is. Okay, so what I need is whatever is on the left. So I'm going to do E prime prime, J, X, S prime prime. Actually, do I really need to specify all these separately? They're all reactances, so what can I do with them? Make life a little simpler. What I'm going to do is this. I have one reactance over here, which is J times XS prime prime plus, I have no idea what the other two are named. This is sequence 1. What is it? Oh, the problem isn't up there anymore. You can't answer the question because the problem's not there. There we go. So XD and XL. Don't know what XD and XL necessarily represent. XD1 plus XL1. And let's call this X left 1. Okay?
Question?
Yeah.
Why did you put the XS1 like with the prime?
Because we have to use the subtransient synchronous reactance. And the prime is designating it's the subtransient synchronous reactance. So we have to look that number up, say in Bob or Luca's book.
So that's specifically for the source?
Yeah.
Okay.
Yeah.
Because I'm used to seeing it like in the notes, I have like ZG or XG.
ZE with prime?
Yeah.
Yeah. So the reason for that is because we're using the, and it's not just for the first sequence, it's for the second, negative sequence and the zero sequence as well. They're all prime, as I recall. Yeah. And they're different for the different sequences, or could be. Okay. Then I have a fault. This is where the fault is, and what's to the right of the fault? Just a resistor, R load. And it doesn't say that R load is the same for all, so we're going to draw R load 1. Okay? That's the first sequence. What's the second sequence? Or the negative sequence? No source, right? J times XS2 prime plus XD2 plus XL2, like that. And let's call all of this X left 2, just to make life easier, I'll put J from it as well. Okay, then we have the fault point. And we have the fault point, then we have the R load 2, like that. Okay, then we have the zero sequence. This is JX S prime 0 plus X is D0 plus XL 0, like that. And there's my fault point, and there is R load 0. So clearly, there's a whole lot of stuff we're not doing here, like figuring out what those impedances actually are. But there are the three. Now I have to figure out how I'm going to hook them together. So I'm looking at this thing right here. Do I really need to think about anything over here? I'm already taking care of that. That's just our load, right? So here's this. It looks like I have a ZF between the top and the bottom, the top of the positive sequence and the top of the negative sequence. And then I hook these two together. And this over here, what is that? No connection. So did I actually have to draw that?
Hopefully not.
Nope. So we probably didn't need to draw this. So I have between here and here, what do I put here? Was it 3ZF? Okay. And I could probably make this a little simpler by drawing it this way. And then what else do I need? I need one from here to here. I'm going to draw that over here. Is that the same circuit? Yeah, it's pretty much the same circuit, right? Yeah.
Isn't it to the top?
Yeah, shouldn't the ZF be on top of there?
Oh, yeah. You were absolutely right. So is that ZF or is that 3ZF? Just ZF? Which is, in this case, what? Oh, we don't know what ZF is. I'm sorry. We don't know. It's not been given to us. There's our fault impedance right here. So from here on, it's just a circuits problem. But what are we actually trying to find in our circuits problem? Yeah, the fault current. Now, the fault current is which current? It's the current that's flowing between line B and C. So it's either IB or it's IC. You don't have to specify one or the other. Okay, does your green sheet give you any hints about which of the IA 1s and 0s and everything else we have to find in order to find that? Or are we going to have to put them in the matrix and figure them out that way?
It says J keep root at 3
Times. Okay, so what's the only thing we need to find? IA1. That's it. I only need to find IA1. I don't need to find IA0 because it's 0 anyway. I don't need to find IA2. By the way, what is IA2?
Negative IA1.
It's negative IA1. Okay. So, Ian, where in this drawing is IA1?
IA1 is right next to our load going right to the, yeah.
It's right there. This is IA1. What is this current right here?
IA2.
That's IA2. And that's why IA2 is equal to negative IA1. Because it just goes up through ZF and then back, right? Okay, there's a couple of ways you can do this now. You can run the whole equation to figure out IA1 if you wanted to. It's easy to get messed up. Or you can do except have an equivalence of the various circuits and do that. Or you can do, combine some impedances and maybe make it easier that way. What do you think you'd like to do?
I have a question.
Yeah.
Would you accept if, like, instead of putting in the 1 over, like adding them all in parallel?
2 lines for parallel?
Yeah, just like 2 lines in parallel?
Yeah, I think I would. Yeah, I would. It makes life a little easier. I'm trying to think, do I want you to tell me what the 2 lines mean at some point? Hopefully you know that. All right. So what if I combined all those impedances in the bottom, the negative sequence circuit? What would that suddenly look like here? If I combine these two. This looks like a single impedance of how big? So what should we call it? Call it Z2? V2, right? What do we call Z2? So it's basically the impedance from this point to this point, which is what? Well, I'm just going to put them all in there. Okay, and notice once I've got that defined, I can now use it in other equations, other relationships. So that's why I say you're going to give me expression or expressions. And now make sure they're in some order that makes sense so I can figure out what the hell you're doing. Because everybody's answer could be somewhat different. Okay, so that now essentially looks like this circuit. Is that now the circuit? So yeah, you have to be able to see these circuits and simplify them either in your head or by redrawing them in some simple way like this. And what's the current we're looking for here? So let's define this current right here and then we'll do a current divider. How's that? IS. So what is IS?
Double prime over KX left.
Divided by JX left 1 plus. But one thing I want to ask you though, how long did it take me to draw this drawing? Virtually nothing. a lot clearer what to do? So don't be shy about redrawing your circuit. And there's two advantages to that. One is that it makes it easier for you to see what to do next. Two is it makes it easier for me to see what the heck was going through your brain, so that if you do it wrong, I'm not lost and have to take the go, whatever, lots of points off. I can say, oh, that's the mistake this person made. They put this in parallel with that instead of in series. Now I understand. Whatever. Okay, so what are we doing now? We're doing the parallel combination of and because I've defined Z2 over here, I can use it over there. Okay, now I have IS. How do I figure IA1? What is IA1? It's IS times what? Now, I'll let you do your, no, we're going to do this way. Okay, let's do this. Oh gosh. 1 over ZF plus Z2 divided by 1 over R load 1 plus 1 over ZF plus Z2, like that. Is that a current divider equation? Yeah, that's a current divider, isn't it? Or I could have found the voltage. Could I have found the voltage across R load 1 and then used it to find IA1? Yeah. That might have been even easier. So there's many, many different possible solutions to this. I could have also found the Thevenin equivalency of each of the circuits. Now the Thevenin equivalent of the second circuit is just, that would be Z Thevenin 2 right there, the Z2. And there is no E for the positive or negative sequence. For the positive sequence, I would have found an E Thevenin and R load 1 in parallel with JX left 1 would have been the E Thevenin for that. So yeah, I can do various things. But I left a little room in front of that. Anybody know why?
Still number 3.
Yeah. So I want to find the fault current, and I'm going to define that as IB in this case. So I very clearly label that as IB is equal to the square root of 3 times this. And what's the angle? Isn't there an angle thing too? Now, what is it for IB? Because it's different for IC, and I think the thing that you have there it says IC first, right? So what is it for IB? Negative J 90 degrees. So can I do this?
You can't say J 90 degrees. That's not how it works.
What, did I do something wrong? Really?
It's J or 90 degrees.
Yeah, so I just did the, yeah, I didn't even put the J. Did I? Is my thing on J, on the?
No, it's not.
No? Okay. So, I don't know, is that right? I don't have the green sheet. I have a green sheet right here. Anybody need another one?
They say that IC equals that, and IB equals
IC is J times the square root of 3. So J is 90 degrees. If I make it negative 90 degrees, it's negative.
But the D and C don't, like IB and IC don't matter.
I don't care. If you give me IC, that's the fault current as well. It's just the fault current in the other one. I don't care. Either way, it's right. Because two lines are connected to this fault, we can define it either way. So if you wanted to say this, right? That is just as good. Make sense?
Would you ever put a double line open on it?
Yeah. Why not? I think I did. I think I did this in either fall or spring of 24.
Make me sad, that's why.
But everything's in series. There's a double line open. It's not that hard.
It isn't actually that bad.
Yeah.
Let me pull it up here in a second. Okay, is there anything else we need to do on this problem? Yeah, make it show up again on the screen. How about that? Here's my mouse. I think I just made a wiggle this sucker.
Would you mind uploading Spring 24?
Pardon?
I don't see Spring 24.
Oh, if you have, if you downloaded the stuff, I think before the weekend? I don't remember when I put it up. There's something, somewhere over the weekend, I think I added it to this.
I looked today, I should see it.
Just refresh.
Okay, because I thought it was up there. I don't have a clue. Do that. How about, is it in the finals all C? Did you look at the finals all C? C meaning there was an A and a B, which is older tests.
Yeah, it's in there.
It's in there.
Yeah, it's in the
Both
zip
fall
file.
and spring 24?
Yeah, it's in the zip file, it's just not on the website, like individually.
Oh, okay. Well, I thought I had uploaded that. Thank you. No, wait a minute. Are you on the screen right now, or?
Yeah.
Okay,
Yeah.
do a reload. Do a little reload on your computer, on your browser. Because it might be that because it's something you looked at before, it's been a little.
No, it's in the zip file though.
It's in the zip file, but not on. Yeah, I gotta fix that. Thank you for letting me know. All right. Anything else I need to find out on this? Set up the circuit you need to analyze. I have no idea. I can't find my stupid stuff. There it is. See, some things it makes it easy, and other things it's not so easy. Okay, that's it. So the question then is that tough a problem? No, I'm not trying to make it that tough. I'm trying to get you to think at it, look at it, do some thinking, stuff like that, and that makes it stick in your brain a little bit longer. Because some of you already have an internship this semester, this summer, and you know for an interview next year sometime, and they ask you about this. Hopefully, there's still a little remnant of it in your brain. That's the hope. So I make it work. Spring 24, fall 24. Let me do that real quick. Nope, that's not the one. Okay. Spring 24. Oh, they're coming to get us. Okay. All right, for Riley. Spring 24, right there. Riley, I said, this is the circuit right here. I said there was an open at F right there. I want you to notice something else about this problem from Spring 24 as versus the problem that I just did. The problem I did there was worth 22 points. The Spring 24 problem was worth 40 points. So yeah, there's a little more work involved in this one. A little more work, a little more time. You can expect that. Okay, so what did I have here? I had, let's see, point F, there was a double fault occurrence, point else, lines B and C are both open. So now we've got to figure out this stuff. And I've given you a grundle of numbers just to make your life miserable. All of these numbers right here. A lot of them are similar, but not all. So in this case, you had to draw this circuit where everything is in series. So there's a little more drawing involved. But once you have that, it should be noted that I can't find my mouse again. There it is. The current, there's only one current in this. It goes out through this, here, around this loop, out through here, around this loop, up through here, around the back. So by the time you're doing the math on this, it's not that awfully bad. I just put everything in the series. Right? And then I did some math on it. Yeah. But this one was probably the hardest one I've ever given. Because, not because it's that difficult, but because there's some bookkeeping involved in putting all the numbers together. And then once you had the numbers, you had to kind of run these things through this matrix to figure out what the answers were. But that's probably the worst one. Who asked the question first? It was you? Yeah. I have time. So there's cases like that where sometimes and it's not unusual that one of the problems on the test is a little harder than the others. You probably noticed that on all the tests. Has something that's a little bit different, a little bit screwy. Because I'm trying to show you that you know what you know.
Could you scroll up to part A?
Oh, you want to take a picture, do you? Please do not post it on the web. Would you like me to turn off the lights?
Yes, please.
Well, they're taking their own sweet time. Like they're not doing it at all. There. Now, respond to my button. All right, I am ready for another question.
From the previous exams, like 1, 2, and 3, what are the problems that you're most likely that you're leaning more towards putting on the line?
Honestly, I haven't thought about it yet.
I would really hate it if you put a single phase.
What's that?
I would really hate it if you put a single phase power problem on it. So,
No, I have to keep that in mind. I don't want to disappoint Madeline. Yes.
Can we do number 1 from fall 23, the power flow?
Same test I got open before, right? This one? Oh, this one?
yeah.
Okay. This one can go. All right. I wish I had where you write on that. This would be a lot easier to write on. Because I sure as hell don't want to redraw it. Kind of lazy. Let's see. Can I do that? Yeah, I can open it up in X journal, but I can't write very well. All right, let's go here first. Identify each bus as slack, load, or generator. How are they different? What do we know about the slack bus?
Is that one with the squiggly thing?
Yeah, that's typically how I show it. There's nothing, that's not really a standard that anyone else might use. I try to keep that kind of standard, yes.
It's usually the one that has 1 per unit.
Yeah, it has the 1 at 0 per unit because the voltage at your slack bus is considered your reference. So if you see something with a 1 at 0 per unit, yes, it probably will look like this just because that's the way I tend to do it. But it is the 1 per unit really gives it away. Okay, and we don't know the P and Q there either because they are things that we can figure out. At this point, Rob, you might just want to take it over and set it between Peter and Kiva because I'm going to be over here for a bit.
You're just going to be over here?
I'm not going to draw this up. I will catch, the board about this much to do some of the matrix stuff. Peter could probably set it up for you. Okay. Ryland, or Nate better be happy with that. Anyhow. Are we ready? Okay. So, we decided that this one was the slack. So, you write slack here for bus 2. Bus 1, we have P, and they're coming out of this bus. Therefore, what would we consider this type of bus? So that is a load bus right there. Now, I'd like to take my pen and write up there on the screen, but I think they'd be upset with me, the university.
So here, another one, an output power and a lagging power factor. So what is bus 5? Almost certain. A load. So bus 5 is a load right here. Let's see, 4, we have an S out again. That's a load. So this is a load right here. And then 3, looks like I have an input mechanical power. If I'm putting in mechanical power, what is this item right here? Generator. And we know what the voltage is, and we know how much P in, I guess, is to, at least within some losses. So we have an input power as well. So what is this guy right here? Generator. So it was load, slack, generator, load, load. All right. Show V1, V3, V4, V5 on the drawing. V2 is already drawn. So all you have to do is put a little V1 right here, a little V3 right here, a little V4 right here, a little V5 right here. That's all I'm going to do. That's it. All I got to do. Show the eyes. The key to the currents are what? They need direction arrows. What are all the direction arrows?
Inward to bus. From the outside, I guess.
Yeah. So they all come into the bus. So I need to draw an arrow coming in, and that is I2. I need to draw an arrow going in, and that is I1. I need to draw an arrow coming in, that is I5, blah, blah, blah. Okay. So let me change my drawing here. Is this the same one? Okay. So it was on the same test as this one, wasn't it? So to make sure we got all that right.
That's a different test.
Is it?
Yeah.
Okay, which test was this one then we were just looking at? What's that?
Fall 22.
Fall 23? All right, so we should have something that looks like this. And you're asked to put those things on there. And notice all the currents are in. All the currents are in. Current 1 is in, current 2 is in, current 3 is in, current 4 is in, current 5 is in. Now, by the way, the powers have to be in as well, so we would make those negative if we needed to use them for anything. Okay, what is this matrix called right here? It's the admittance matrix. And I put this on here, and I think you have something similar like that on your green sheet, don't you? So you can keep in mind what's Y11 and Y22 and all that junk. Yeah, you have a very simple one right there. Yeah, okay. And notice load, slack, gen, load, load. So now we have to go in and figure out these things here. Show the 5x5 matrix. What is it called? E. Number of the elements are 0. How do you find the 0 elements? Okay. So you look at number 1 here. Because 1 will give us this top row right here. 1 is, of course, connected to 1. 1 is connected to 2. Connected to 2. It is not connected to 3. It is not connected to 4. It is only connected to 5. So what we have here is, what the heck happened here?
Yeah, 3 and 4.
Oh, yeah, it is connected to 2. It is not connected to 3, it is not connected to 4. Those are the zeros. So, number 2, let's see, 2. It is connected to 1, it is connected to itself, it is connected to 3. It's connected to 1, itself, and 3. It is not connected to 4, it is not connected to 5. These two are 0. Yes, Amy?
Oh, never mind, I'm just doing that.
Oh, okay. I3. So we go to bus 3. Bus 3. Now, generally, I will number the buses so everybody gets the same answers. Otherwise, life gets really weird. Okay, 3 is connected to 2, but it's not connected to 1. It's connected to 2. It's connected to... it's connected to 4. It is connected to 5. Whoops, there. And is it connected to itself? Oh yeah. No, that's B. A is 4 connected to 3. Is 4 connected to 3? Yeah, exactly. Right there is 4 is connected to 3. Okay. The other two can be figured out in the same way, or you can just dig it. It's got to be a symmetric matrix about the diagonal. So if you have blank, blank, 0, 0, blank, then you got a blank, blank, 0, 0, blank down this way. If you have blank, 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 0, 0, you can have blank, 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 0, 0. In your case, you would just fill in those blanks with zeros. Okay, so anything that's not connected. So now we have to figure out A and B. What do we do for A? A is between which two? Between 3 and 4. So it's all this yuck right here. Kind of.
1 over Z.
Yeah. So what do we have to do with that? For that one? Hmm? It's got to be 1 over what?
0, 2, 0, 4 plus 0.
Does this show up?
No.
Does this show up?
No.
It's just got to be 1 over this, doesn't it? But not perfectly just 1 over this. What else? Negative 1 over that. So A is negative 1 over this. So you're going to have to do some complex arithmetic to come up with that. And the process, I'll show you the process here in a second. I'll show you the numbers in a second. What do we have to do for the B? Is B, one of them's going to be on the diagonal, for sure. Is B on the diagonal?
Yeah.
So it is for 4 right here. How do I know it's for the 4th bus?
Fourth row, fourth column.
Yeah, it's 4th row, 4th column, right there. So what do I have to do with this? It's got to be,
The soonest one in any direction.
yeah, I have to do all of the y's. So there's not a y given to me here, so what do I have to do with that?
1 over Z.
1 over z plus
Plus Y.
Plus
1 over that again,
Oh, yeah.
plus,
Plus the closest y.
yeah, do I have to do a 1 over the 8j?
No.
0.08j, right? Why is it 0.08j? Okay, so now let's go see what the answers really were. So let's see, the Z34, that was this one up here, right? That's the Z34, that's this, so I've identified that. A is just 1 over that with a negative sign in front of it, and this is what I get. That's all there is to it. B, we get the, Y34, we get,
Yeah, that's the
yeah, Y34 is this one right, why did I call that Y34 there? And that's the 0.08J. Okay, well, this is the Y34, I guess. So that's that. So that's the 0.08J. 1 over, again, the exact same thing we did here, and then 1 over this one right here, Z45. The Z is between 4 and 5. So that is not the best way to enumerate that, because that's not the same as that, which is confusing. So that, my terminology is not the best in this. And then you got to do some complex arithmetic and come up with that.
And that's about as deep as I go into this. I'm not trying to strain you too much. What I'm trying to do is to see if you've spent a little time with this, know a little bit about it. So if you go on an interview with Kent Newman and he asks you about power flow problems, you have some idea what they involve and that sort of thing.
You said fall 23 final was a good one to look at the no-no sheet part.
I don't know.
I think just all of them.
Yeah, just look at all of them. Is there anything else anybody would like to talk about or ask about?
When are you writing the exam? So you get
Could you say that again?
When are you writing the exam?
Oh, you want to send me flowers?
Good.
Probably tomorrow. Try to get to it. What I try to do is have everything pretty much in place and ready to go tomorrow. And then on the morning of, I go through it again and check it.
Aaron, when you're doing just the one bus, you don't need the negative sign?
Okay, if you're doing on the diagonal, there's no negative sign. But anything off the diagonal, there's a negative sign before you flip it over. I think that's what you're really asking me. All right, I will try to keep my phone handy. I don't always have my phone handy. If you call me about a question or something like that and I don't respond within 15 or 20 minutes, try it again. Just repeat the same message until I pick this stupid thing up. Because right now it's in my backpack silent, and if I don't remember to pick it off silent, I won't hear any of you. So maybe that's not something. Okay. Anything else anybody else wants to talk to me about? Ask about. All right. I will see you on Friday, folks.